Exercise 7. DC motor PI velocity control. So proportional integral velocity control.
Pi.
Oh yes, not pi. Pi velocity control would probably be a whole different thing that I don't even know, but it would be cool, no doubt. So the objectives of this exercise are to incorporate many of the hardware and software elements developed previously in this course into an integrated closed-loop control system. Yeah. 2, implement a program structure allowing continuous modification of the control parameters without halting the control algorithm, which is pretty cool. So it's not like you deploy it with certain gains in it or something like that, and that's all it is. You can actually use the keypad and the LCD screen to edit your controller gains, which is pretty fun. And then finally, implement a proportional integral PI velocity control algorithm for the DC motor.
This proportional integral velocity control algorithm, it means that the speed is...
Well, we'll talk a little bit about what it means. I'm not planning on going into detail on that, but if you're interested, so let's see. Next week, I won't quite be lecturing on it, but I could send you a couple lectures on this type of control. From the system dynamics and control course that I've taught before. So I can send a lecture or two out to people. Those of you who are...
Last year's on YouTube? Last year's on YouTube.
I think last year's are on YouTube, so you should get... I think there is PI from last year. I think PI was one of the examples I did last year, so yeah.
I know you did PID.
Cool.
Yeah.
So I probably did PI. So we'll look and see what I did before, and they send you a lecture. But I'm assuming that you know how to do this, but I also recognize that Martine is in that class right now, and I don't know what your control background is. So we'll do some supplementary discussions on this, but the controller type. It's a pretty simple type of controller, pretty intuitive, and actually very common controller. So it's really useful, even though it's rather simple. So we'll get into it. Essentially, what this is describing is what transfer function do you want to have that MyRio behave like. So you know how last week we learned how to, in Lab 6, we learned how to make it behave like a very specific filter. Well, that filter is going to be a PI controller transfer function. So, yeah. And you don't have to actually derive it. I kind of give the transfer function to you. So we'll get into it. It's pretty cool. So, intro. In this exercise, a closed-loop control system for the DC motor will be developed. The system is similar to actuators used in many types of positioning systems. The primary drive of one axis of an automated machine tool, for instance, so like a milling machine, like a CAM-based concept, or one axis of an industrial robot. These are often computer-controlled DC motor actuated joints. So really useful to be able to do this type of control. A lot of applications for it. Our system will control the motor speed. And in fact, I would go so far as to say that like 90% of things that an ME is typically going to want to control is the speed or position of a motor, of a DC motor. That's like a lot of times, that's what it does. Okay, so the control algorithm will repeatedly compare the actual velocity of the motor, or what really is the measured velocity of the motor, so V actual, with the desired reference velocity, V ref, and automatically alter the applied control voltage to correct any differences. Although this is not a trivial computer control task, you have developed nearly all the required elements in the preceding 6 exercises, so you don't need to reinvent any of those. You can just sort of like take this, and then bring them together. So the optical encoder through the FPGA, the D to A converter connected to the motor amplifier, and the periodic timer interrupt will be combined to control the DC motor. As in so lecture B6 is the lab exercise B6. I don't know why it's saying lecture instead of lab. I can do it. A separate timer thread will be produced. Will produce an interrupt at the end of each BTI. The ISR, the interrupt service routine, will load the IRQ timer write and IRQ timer set time registers to schedule the next BTI, and then call functions to read the encoder. So this is like same thing before. So as before. So you're going through this loop, this timed loop, right? And your interrupt service routine has certain tasks that it does. Remember, we just have to make sure those tasks complete before the next interrupt would come. Otherwise, we're in trouble. But if we, as long as we keep those tasks short enough, they execute quickly enough, our loop will be timed no matter how much time those tasks take. So, and then we're going to do these three things this time. So the first thing we did in lab 6 was we read the voltage in, and then to analog in, and then we first just wrote that right back out, right? So we, in and then out, and then when we put that through the cascade function to implement the filter, right? We're gonna do the same thing, but we're gonna do like a couple extra things too. Only things that we've done before though. So we're gonna read the encoder counter and compute the velocity. So we've already done that before. We're gonna execute the motor control algorithm, which is essentially to use the cascade function to run it through the filter. And then we're gonna save the results as necessary. So in certain circumstances, we're going to want to save these data points so that we can later in MATLAB have a nice response curve that is the theory, and then we're going to have the experiment. Oh, it's going to be cool. So the control system will be table driven. That is, the parameters used by the control algorithm, reference speed, system gains, and BTI length, will be kept in a special table of values. Through the keypad and LCD, the values of the parameters in the table will be altered interactively by a table editor function called from the main program thread. The only task of the table editor will be to change the table values in response to commands from the keypad and to display performance information. So there's this separate table editor thing that's going to be running that we can go in and change what's the proportional gain or what's the BTI length. And then the controller is going to always refer back to these spots in memory for those parameters. So they'll change while it's running. So you can change all this stuff while it's running. So it should be pretty cool. This table-driven structure will allow the program user to change any of the control parameters. It will appear as though two programs, the table editor and the control algorithm, are executing simultaneously, when in fact we've got this interrupt service routine is how it's working, right? So it's not two separate programs. It's just got two threads going on, the main thread and the ISR. You will not write the table editor. Previous instantiations of this course had the table editor function as one of the tasks to write, and it's not that hard, it's just really tedious. So the required function, ctable2, is described in resource C8, so you can check it out. To understand how it works better and to use it, it is very helpful to go through that resource. It has been included in the library though, so the ME477 library has got it, so you don't need to write it, and it's automatically linked with your program. Although you will not write this function, It uses the basic keypad display algorithms that you developed in exercises 1 through 3. The prototype for CTable 2 is in the header file, CTable 2. The motor will be controlled using a proportional plus integral, or PI, control law, as shown in figure B12. So this is our control law. So this is like the basic block diagram of the control loop. We're gonna get into a more detailed one at the end of the lecture, but this one gives you an idea of how this works. So you have the motor that has some actual velocity that is going to be measured through, I guess you could think of it as being a voltage. Gets fed back and compared to what the velocity should be in terms of the voltage that it represents. And those details will be worked out in the other block diagram. It gets compared to this reference by subtraction. If you subtract it and it's the same, so like if the output velocity is the command velocity, this is called the command, the reference. If they're the same, the error is 0, and the transfer function taking in a 0 is always going to return 0. So you wouldn't do anything. So no control goes to the motor. However, if there is error, if there is a difference between the reference and the measured value, then there is some non-zero error, and this controller, this transfer function, acts on it. And it has two terms that it uses to act on it. A proportional term, which is proportional to the error. And so like if your error is, 1 radian per second, then it's going to be 1 times whatever your proportional gain is of actuation to the motor to try to make it happen. So the further away, the larger your error is, you have some proportional response from the controller. The integral one is controlled by this term. So 1 over s in the Laplace domain is your integrator, right? So integrating the error means that you're keeping track of it over time. So usually there's a window of time that you take it over. So this is like the current time, t now. This is like the initial time, t naught. And the integral term is proportional to the integral of all of that. So this is really nice for fixing steady state error, because even if you have a small steady state error over a while, it accumulates and will give you a good response. This is a pretty safe type of controller. PI, there's not too much that can go wrong with it. When you add the D in there for PID control, it gets a little bit more dangerous. There's a lot more chance you're going to go unstable. And we can talk about why that is, but it's essentially because the derivative estimation is very prone to, you have your measurement data points of your error coming in, and then like maybe it's noisy or something weird happens, and suddenly there's like a point that comes in that's way down here. Your derivatives are the slopes, right? Slopes are, pretty pedestrian slopes, and then suddenly you've got this slope, right? It just falls off at a rapid rate. And so suddenly you would have this huge response that you would put into the motor using your amplifier, and you would drive it with a ton of current. And one thing that happens a lot with this is that you'll see jitter. So it'll go back and forth rapidly, just because it'll push it. So say you're too far right, it'll push it left, and then you're too far left, so it pushes it right, and then it just goes back and forth rapidly. So that is the problem with derivative. Not that we shouldn't use it, because derivative can be very helpful, but we have to be more careful with it. It's very safe to leave derivative out and just say integral, it grows over time. But integral has its own problems. You have integral wind up, so if you have it accumulate for too long, you don't have a window on it that forgets old stuff, it could be reacting to something that happened a while ago, which is not always what you want. So you can get this integral wind up, and it'll fly the other directions. Like say it's too far right for a while, it accumulates, and then suddenly like maybe some obstruction is removed or whatever. It's got all this integral wind up built up, and then it just way overcorrects. So you got to watch out for that too. Okay, so PID control, PI control in this case, really useful, and maybe we'll have some supplementary discussions on PID control. Okay, so where were we? C table 2, yes. Good. The PI control law relates the error to the output control signal U using the gain constants P, Kp and Ki. Applying Tustin's method to the continuous controller transfer function, which is Kp plus Ki over S, the corresponding discrete transfer function is B8, which is actually given in that table from whatever that lecture was, 4 whatever, the one on discrete control. And when you discretize the transfer function, remember it goes from being in the Laplace domain to the Z domain. Instead of having Laplace transforms, you have Z transforms. So this is the transfer function. And here are the constants and the coefficients in it. So B0, B1, A0, A1 are listed below. Some of them are numerical, others are in terms of the Kp and the Ki, and T, which is the sample time. The error is going to be the difference between a reference and the actual value. For more on Tustin's method, go back to, it's 4.4. That's the section on it. You will implement the corresponding difference equation using the general purpose algorithm you developed in lab exercise 6. So we already learned how to implement one of these. Not a controller in that case, but it was a transfer function. It was another dynamic system that was just a filter, right? Now we're going to be using a specific transfer function that's designed to be a controller for our system. So, pre-lab prep. Drawing on your previous work, write 2 threads. 1 to communicate with the user, and 2 to control the motor. So, it's pretty common. We've been doing this for a while, right? Main and then the thread to service the interrupts. Main program thread. The main program performs 3 tasks. It initializes the table editor variables, sets up the and enables the timer IRQ interrupt, as in lab exercise 6. 3, as in lab exercise 6, register the timer thread and create the thread to catch the timer interrupt. In this lab, the timer thread will gain access to the table data through a pointer. So this is something that we do need from main, right? We need to be able to know what's in the table. So we do that by giving it a pointer. Modify the timer thread resource to include a pointer to the table. For example, this might be a good idea for modifying the thread resource. So, and notice you see here, there's a line that wasn't the same as, it's not the same as the others, and it's this line here. It has the table in it. Okay, well, it has a pointer to the table, because you know you can't pass tables because it's C. Because it's C. So call the table editor, which is the C table 2 function, right? The table should contain 6 values labeled as shown. So it should contain vref, v actual. So in RPM, vref, and in RPM, v actual. So velocity reference, velocity actual. VDA out in millivolts, which is the output analog voltage, and KP, which is the proportional controller gain, KI, which is the integral controller gain, and then BTI in milliseconds. All the table edit values should be initialized to 0 except the BTI length, which should be 5 milliseconds. And note, use these units because it is a pain to have to, like, if you are going to enter the BTI, for instance, in seconds, you don't want to have to do like 0.00000 1 seconds. It's in milliseconds. And these are in RPM, and that's really common when you have a controller in like an industrial setting. Like, oh, I want this to be a certain speed. Most of the time, people are going to want to enter that in RPM, rotations per minute, not in radians per second, which is the SI way of describing it. So I'm going to keep in mind. Good. When the table editor exits, it signals the timer thread to terminate, using the same mechanism we've done previously in main. When remember in the past we hit delete, and then it ended the thread service thread. So then we'll do the timer thread, the ISR. The beginning of the starting function, declare convenient names for the table entries from the table pointer. So here's one way to do that. What it's doing is it's giving a name, so you don't have to remember what position in the table each of these is. Giving it a name makes it easier to use when you're in the thread. I recommend it. Technically, you don't have to do that, but I think it's going to help, especially when you know we're going to have to debug that, and it's going to be really hard to debug that when it's like, oh, what was the 5th element in the table? I don't remember. If you give it a name, that helps. So, as in lab exercise 6, the timer thread includes a main loop timed by the IRQ and is terminated only by its ready flag. Before the loop begins, initialize the analog input and output and set the motor voltage to 0 using AIO write. Set up the encoder counter interface, as in lab exercise 4. Each time through the loop, it should get ready for the next interrupt by waiting for the IRQ to assert, writing the time right register, and writing true to the timer set time register, which is same as before. Calling vel, which is what we did in lab exercise 4, to measure the velocity of the motor, compute the current coefficients, the A's and B's, for the PI control law from the current values of KP and KI. So remember, it's essentially what we were doing previously, but remember that our biquad, the A's and B's in our biquad never changed in lab 6. Now they change if the stuff in the table changes. So that's one variation on what we did before. Because remember, just the X's and the Y's changed.
Yeah.
Now we have the A's and the B's can change too. And then update the values of the biquad structure. Compute the current error, so take the difference between the reference and the actual. Call cascade to compute the control value from the current error using the difference equation for PI control law. Important, limit the computed control value to the range -7.5 to +7.5 volts. It's possible that we're going to saturate our control output. So our control output will sometimes be computed to be like, 50 volts, but we don't have 50 volts, so we're going to have to saturate that. So we could remember, just like last time, if it says to do 50 volts, we can't actually put it out, and it would just put out the 7.5. But if we limit this in the code, then the values that we dump out and the previous values will be correct and not be, it's like it computes it based on the previous input, it won't be an incorrect value. It won't have actually put in 50 volts. So you don't want it to think it put in 50 volts. So there's that. Then send the control value to the D to A converter. The 0, so the C channel's analog output 0. C channel, not A, the C channel. Using AIO right. Change the show values in the table to reflect the current conditions of the controller. Whew. Then save the results of this BTI for later analysis. And we'll see, I'll talk about the MATLAB save a little bit. And then acknowledge the interrupt. So it's like kind of like nothing new, just like all of it in one.
A more interactive and complete system.
Yeah.
Yes, because it's only make use all of the things, the keypad, the display, the motor, and other interrupts that we learned.
Got it all happening. It's all coming together. So the functions are, so the cascade function, called once from the ISR during each BTI, implements the difference equation algorithm from lab 6. For this lab, use the same C code that you used in lab exercise 4. In this case, the number of biquad sections will be 1. I think this is a typo. I believe this should be lab exercise 6. Yeah. Note that, as in lab exercise 6, all calculations should be made in double floating point arithmetic. Vel, using the vel function developed in lab exercise 4, there's the 4, that's correct, to read the encoder counter and estimate the angular velocity in units of BDI per BTI. And then remember, we converted that to RPM. So we can work in RPM. Okay, then saving, which is another thing we've done, right? But I'll talk about when to save and where to put that in your code. But we already know how to do that process. So a convenient method of saving the data is to define data arrays in the ISR for both the velocity and the torque. Then an auto-incremented index variable is used to store the data in the arrays during each BTI. Increment the index as needed, stopping when the index reaches the length of the arrays. A convenient length would be 250 points each, just based on our BTI. Since our program runs continuously, you may wish to save the response whenever the reference velocity is changed. So you could have like a separate button if you wanted to like do an interrupt on it that initiated the save. But we're going to be mostly interested in step responses. So what we're going to do is we're just going to, whenever the reference velocity changes, so say it's going at 1500 RPMs, that's the set. And you say, if you type in 1800 RPM as the new set, and you hit enter, it starts filling up for 250 points, and then it's done. If you change the reference again, so say like 0 RPM or something like that, and it's like responds, it'll start taking data, it'll overwrite it. So it's just gonna write, it's gonna keep overwriting the 250 point buffer, as whenever you change the reference velocity. Yeah, so it's easy to accomplish by checking to see if the reference velocity has changed since the last BTI. and resetting the index to 0 if it has. Since the index is then less than the length of the arrays will be refilled. This is equivalent to recording the step response input in the reference velocity. In addition, when the ISR resets the index to 0, save the previous value of the reference velocity. You want to know what the velocity reference started at, right? So like you don't want to forget, so like the new reference velocity is important information for the step response, but also what the old reference velocity was. So if you're going from 1500 to 1800, you want to know where you started. So we want to save the old reference. So we want to keep track of the last reference velocity and the current reference velocity. And those values, along with other system parameters, will be used in MATLAB to predict the theoretical model response. Okay. After the main loop terminates, but while still in the timer thread, write the results to the lab7.mat file. The results should include your name as a string, the actual velocity array, the torque array, the current, and the last previous reference velocities. Last and previous reference velocities. So remember, like 1500 and 1800. Also, there's three more: Kp, the proportional gain; Ki, the integral gain; and the BTI length. As this, use the same methods as lab exercise 4 and 6 to bring the lab7.mat file to MATLAB. So you guys have done that process already, so it shouldn't be.
We haven't seen this MATLAB.h, the header file in the lab 6.
Yeah, it should be in lab 7, the MATLAB, and it was in lab 6 and it was in lab 4, so it should also be in lab 7.
I don't think it is in lab 6, because when you try to bring it in, like put the include thing, it says it's a fatal.
Huh? Did you just copy it from the other one then?
Yeah, I copy pasted, but then it didn't show up anywhere.
We'll take a look after this. It should be in there. Mysterious. I'll take a look when we go over there. We're almost there, so. So for the lab procedure, do your typical testing and debugging. Use the base set of controller parameters in your debugging. So this table right here gives a base set. So set your BTI length to 5 milliseconds, VREF to plus or minus 200 RPM, KP 0.1, KI 2. While the motor is at steady state speed, gently apply a steady load torque to the motor shaft. What are the responses of the actual speed and control voltage? Explain. So this is like, the flywheel is a pretty safe thing to touch. Yeah. Please do not get like your hair or anything like that caught on the motor shaft. It will rip your hair out. It's pretty gross. Don't recommend it. So be safe. Fortunately, I think that's about as dangerous as that motor can get, is wrapping something around it. But just try not to do that. But if you touch the flywheel, so like if you can add a gentle torque to it by touching the flywheel and like slowing it down a little bit, right? So if you do that for a minute, what happens to the steady state speed? So it should slow down, right? You'd think, if you're touching the thing and slowing down the flywheel. And then it should the controller should be trying to make it go faster, right? So you should see that respond. Yeah, so that would be a good thing to test. Then 3, beginning with the base set of parameters, explore the effect of varying the proportional gain Kp on the transient response. Try small Kp and a large Kp. And those are some suggested values. What are the effects on the oscillation frequency and on the damping? Explain in terms of the transfer function parameters. So we should have an ability to explain it from a theoretical point of view when we change Kp and change Ki. And we also want to see that those are actually the case when we change them on the physical system. So that's what 4 is changing Ki and seeing what happens. Then 5, finally, using the base set of parameters, record the control torque and actual voltage responses for a step change in the reference velocity that starts from negative 200 RPM and goes to positive 200 RPM. In MATLAB, compare these experimental responses with the analytical responses for the continuous system approximation. So in MATLAB, you're going to simulate what the continuous system should produce if you instantiate a controller with this Kp, this Ki, and we want to see them match up pretty well. So they should match up pretty well, what the theory says it should be like and what the actual measurement is. Yeah.
So do you mean actual voltage response or velocity response?
So we would convert it to a velocity response, but yeah. So we would back out what the velocity response was, right? So it is like, I mean, we actually measure voltage, but we typically are going to run that through our conversion to speed and say this is our measurement. We should say like the measurement assuming this constant gain between voltage and velocity, which is pretty standard to do. So I mean, the reality is most of the time what we really measure is voltage, like for everything. Like everything we measure is pretty much measured as a voltage. And then we convert that into a representation in terms of something else. With the exception of like, you know, length measurements when we're just using calipers or something. But if it came from like an interferometer or some sort of laser thing, that's also going to come back as a voltage from a photodiode. So voltage is mostly what it is. Yeah. The theoretical responses can be calculated using the approximately scaled MATLAB step command or LSIM command, either one. The analysis should be plotted over the experimental responses. Use the subplot command to place both the control value and the measured velocity plots on the same page. What do you conclude? So, you know, present it in a way that looks nice and that makes sense. I try to give you some guidance, but yeah. Okay, so I'm going to talk now a little bit about what the actual, or what the more detailed control loop looks like. So we've got our controller. We've got a voltage that controller puts out. We're actually going to use the current source amplifier. I borrowed a couple of them, so they're like those big boxes that are on the benchtop now. We're going to use those in these next two labs. So the current source amplifier takes in volts and it gives you current. So it's what's called a voltage controlled current source. You put in, like, so say you increase the voltage that is applied to it, it's going to increase the current that comes out of it. The previous amplifier we were using was a voltage-controlled voltage amplifier, voltage source, which is slightly different. You can kind of do the same stuff, but there are some nice things that we'll talk more about next week, or I guess in 2 weeks, because with doing current control. So current is proportional to the torque. That's the main reason why it's nice. So it goes through the torque constant of the motor, KT, which is given ours. So I'm gonna have to come back to you guys with this value. You guys did this measurement in the lab in ME316 in the fall. So I actually need to go back and look at what I got for it. But yeah, anyways, that I don't think it's 0.11 Newton meters per amp, but it's something not terribly far away from that. But it's a value you'll have. And this is actually a really good number. It tells you that if you have a current running through your motor of some, like say 1 amp, you multiply it by this, and that tells you what the torque that the motor is able to apply at that point. So it corresponds pretty well from the from the current to the torque. So we'll be able to report current and torque. Really, our only thing that we know is we know the voltage, and then there are these K values that tell us, okay, then that means that we have a current of this and a torque of that. So you multiply these things, and then they give you these other parameters, other variables. Then there's the disturbance torque that comes in too. So if this wasn't there, yeah, like when we touch it, that's the disturbance torque. So we have this thing that, so remember it was lab 5, right, that we did the finite state machine, where we were like, okay, let's control this thing to go 1600 RPM. So we'd like say like this, when we did this duty cycle corresponds to this velocity, this one corresponds to that velocity. Well, you can't have a disturbance. It didn't know if there was a disturbance. It just was putting in that voltage. It just went, right? Just went off and did it. But if you put in a disturbance, then this will know that it's not going fast enough. And it will try to speed up. It'll like push more current. It'll try to increase the torque to try to
adjust to the same level of
exactly. It wants to. It's even though you're disturbing it, it wants it to be back to what it's supposed to be. So it's going to fight against the disturbance, which is why control is actually like the foundation of like intelligent systems and artificial intelligence sort of based systems, because it's the sort of the first intelligent thing that we see, right? Like something happens that it wasn't anticipating and it corrects, right? Like it's like, oh, you try to knock it over. Like you guys have all seen, this is a very advanced example, but you guys have all seen those Boston Dynamics robots where they like shove them over and they either catch themselves from falling or they'll come back up, right? Yeah, like those systems appear intelligent to us because they have that sort of feedback loop that they're running. So it's pretty cool.
Yeah, running cheetahs and also these carriage animals.
The big dog and stuff.
Dog.
Yeah. Oh yeah.
It's lifelike.
It is.
Yes.
It's really cool.
Yeah.
So this disturbance torque can come in, and they go into the motor model. So the motor model, we're just going to have a pretty simple model for the motor here. If you felt inclined, there's a more involved motor model that, so J is going to change slightly, so this number will change slightly too. I didn't get a chance to update these. The current source amplifier gain is correct. But J and KT and also B, those are all values that we could use the values that you guys estimated in your lab in 316. And that is a more involved model. That motor model is pretty advanced. If you wanted to use that, that would be fine too. This is a relatively simple one. And then that motor speed comes out. Actually, of course, this is an encoder sending counts to our MyRio, and that MyRio reporting what the count is to us. And then we remember using vel to say, okay, what is that in radians per second? So we get that value back. And then, so then in a certain sense, like really voltage comes out, and then inside the computer we convert that to radians per second. And then we feed that back, compare it to the reference velocity that we want, that the table editor's got in it. And then we put it back into the controller, and the loop continues. Right.
Yes.
Yeah. So fun. Okay. So, yeah. For the accuracy of the approximation, this like continuous approximation, so we could use the discrete approximation to simulate in MATLAB too. So MATLAB will simulate the Tustin method version if we want. If you guys want to do that, that's fine. It doesn't matter to me. But if you want to use the continuous one and you want the approximation to be good, then we need to have the sample frequency much larger than the natural frequency of the system. Time delays caused by computation being insignificant. The control values not saturating, and the mechanical damping B not being small in comparison, or we assume that it is small in comparison with the effects of the proportional KP gain of the controller. So if we make those assumptions, the continuous system should be the same. If we are saturating the output, then it's not going to be accurate. It'll look better, right? Like if in the simulation you could put in 50 volts and it could flow like tons of unrealistic current, then it's going to respond quicker, for instance, than it will actually respond if we saturate. So in order to be realistic in the simulation for saturation, there are different methods of doing that. You can't simply use the LSIM or step functions directly. You have to dig a little bit deeper, set up your ODE solver, like ODE 45 or something like that. And at each time step, you have to, if there's a saturation, you have to actually saturate that. So we're not going to go into that. It's kind of involved. I think that for the specific one that you're going to be comparing, the negative 200 RPM to 200 RPM, with the controller gains that are specified, you shouldn't saturate much, so you shouldn't have a big difference. It should be pretty similar. But that's something that is like the number one annoying thing about simulating, in my mind, about simulating actual control responses is saturated control effort. So saturated control output from the controller. It happens a lot in real systems, and making that happen in the simulation is kind of a pain. I don't know a good way to do it. In MATLAB, it kind of surprises me. Maybe there is a really good way to do it. I just don't know for saturating them. You can do it in, there is an easy way to do it if you do the simulation in Simulink. But I don't really prefer Simulink just because, and it's really nice, but anything graphical, I just don't like it. It just makes me uncomfortable. It's a lot of things, Martine. So, something made me uncomfortable this morning. I can't remember what it was. Oh yeah, it was using. I think it was using. Oh, it was having LSIM MATLAB's function return to you the time array, like that it generated.
Yeah, because you don't know what's really going on. It could be different.
Yeah, like you don't know how big this time array is. Why did you choose this time array? It's
NANs.
what?
It's like using NANs.
NANs, right? Also, you could put zeros in there, but it makes me uncomfortable because like your simulation could give you zeros too. So So there are certain things that I just like to be a certain way. So this is one of them. Okay. Good. So the following transfer functions can be obtained from the block diagram. So I give you those kind of just because there's a lot to do in this lab anyways. So give these to you.
In fact, this one we can derive from.
We could derive them from this block diagram if we wanted to, but so they're given to sort of speed up the process of getting them. So this gives you like the transfer function from changing the reference velocity to the actual or the measured velocity. So this is the closed loop. This is what typically is referred to as the closed loop transfer function. But it also gives us a transfer function to the torque, and it also gives us the transfer function to the control. No, wait. This is the TD. TD. What is TD again? Forgetting. I don't think that was defined. I believe that, oh, here it is. Disturbance torque. It's the disturbance torque to the actual velocity. So this is like telling you how much, like when you slow the flywheel down with your finger, how much you affect it based on the torque that you're applying. And then B12 tells you from a given reference velocity to the control effort. So to U, which is in volts, what our controller will put out. So those are three interesting transfer functions. I would say you're especially interested in this one. And this one is also very interesting too because it tells you how much control effort you're going to want to put out and if that's going to saturate, right? It's like you might want to put out 10 volts, but you only have 7.5 or whatever it is. So you have a transfer function that'll tell you if you change if you have a step input, for instance, in your reference, how much of a step. What does your response look like for the voltage out of the controller? So this is what you would investigate to find out, am I saturating my control? Do I have more space to, be more aggressive with control, potentially? That type of thing. And then, finally, so if we let K equal the current amplifier and the torque constant together. So if we had these two just combined into one, we called it K, then the following values can be used to model the system. In these transfer functions, tau is this, KD is that, KU is that. So it gives you the numerical values for these, which is nice. The natural frequency is this, and the damping is that. So you don't actually have to do the modeling of the system and the motor. The transfer functions are kind of just given to you so that you don't have to spend a ton of time working on the modeling side. Although it's really fun, so if you want to do that, you're welcome to do it. I get a kick out of it at least. So that's pretty much this lab. I mean, there's like a ton, but it's essentially mostly stuff that you've done. I think that there's going to be, I anticipate main problems arising from getting the simulation to match up with your step response values. That would be my guess. But I can help with that. So, yeah. Yeah. Any questions? I mean, we can continue talking about it, but any questions before we sign off and maybe head over to the lab?
Like the only thing slowing down the motor is like the internal friction. It's like always there, right? Like there's no brake.
Right. So it depends. I mean, you could apply a voltage across it in a different way and run current through it against the direction of motion, in which case you would be, I mean, that would be considered like electronic braking. But mechanically, the only thing that is applying any loss to it, so like the flywheel, the moment of inertia of the shaft and the flywheel and the coupler, those store energy, mechanical energy, rotational mechanical energy. But so there will be friction, there will be losses that come in a couple places. The main two places are going to be the bearings that are internal to the motor. So the motor has bearings for the shaft that's inside it. And those produce a little bit of friction. And bearings are fairly well approximated as being linear dampers, so damping comes in through them, and then also the external bearings. So those two places friction comes in approximately as damping. And there are other losses in the system too, and those are electronic losses. So the heat that's generated through the coil, the windings in the motor. Remember, if you drive any current through a resistance, it generates heat, right? And so the more current, even though the winding has low resistance, hopefully, usually it's like a couple ohms for the whole thing. That's enough when you have significant current running through it to generate quite a bit of heat. So it will generate some heat, and that's the other loss. So that's why the efficiency curve for a motor looks like this, where there's a peak efficiency that happens so this is speed. There's a peak efficiency that happens somewhere. So if you go back and look at actually when Dane went through your systems, I don't think, no, mechatronics. You didn't do it in the fall, you did it last year, right?
No, I did both.
Oh, okay. So I went through this fall a very detailed motor analysis where I did the efficiency and stuff. So that has this discussion in it where like there's a peak efficiency where you get maximum power transfer versus losses. But yeah, like on one end you're losing, so when you're up here and when you're going fast, your voltage is high, your current is low in steady state. This is always a steady state curve. And then speed is really high though, so the speed's high. So your damping is the dominant loss that happens. Down here, your speed is low, so damping is low, right? So you don't have much damping loss, but you have high current at low speed. So you have a lot of electrical losses.
I was just curious, like, so when we're controlling it, if, you know, we want it at 1500 RPM and it's at, you know, 1650, are we just turning off the voltage, or are we like reversing the voltage, or is there like a mechanical break in there, or?
Yeah, so it's actually it would try to apply less voltage to the system.
It's not turning it off completely.
So it doesn't turn off. Well, I mean, it might go negative. So it could go positive voltage to negative voltage. So it depends on what the control transfer function puts out. So it might put out a negative voltage when you're going too fast to try to create a torque that goes against. So this would be a negative torque that would be generated. And you would so on the mechanical side over here, although it's still moving in the same direction, the torque is going the opposite direction. So you flip the direction of current flow, and you're driving it the other way. So it doesn't just wait for like the mechanical side to slow down like through damping. It actually actively pushes. Although in position, if you're doing position control, it'll actually go negative. In velocity control, probably it won't go all the way negative, because you're probably going to want the voltage to stay positive. So you're probably going to, you might, I don't know. It just totally depends on your control law. Like it's, what will be interesting to see is, just like with the way that I knew that when I looked at the step responses that they looked funny, was I just did a little simulation, and I was like, well, it should go up to that, right? And we can do the same thing for this, and we can say, well, what should the voltage look like? What should the voltage do? What should the current do when we put in a step input? And that will be a pretty good prediction, probably, of what will happen, unless it would saturate, in which case it would look different after the saturation happened. But yeah. There's nothing out of bounds in terms of this calculation. Like it thinks it can go from an infinitely high number of volts to an infinitely negative number of volts. And so that control law, it doesn't care. I mean, positive, negative, it's totally fine. What you can actually do does depend on the capabilities of your system. And our system's pretty good. Within the range that we're saturating at, we're pretty able to go through that, and it's quite powerful. A lot of times you don't have quite as much power for the demands, and it's like more of a trade-off. We're going to be fine. We have a lot of extra. We're like underdriving everything. It's like over-designed in part so that it doesn't break. Also, it's to be a little safer, because big voltages and big currents and fast speeds tend to be dangerous. So, okay, anything else? Okay, let's head over then.